And I'm tethered here now. Sorry. Yep. This is not good. Do I need this?
I don't think so.
No? Okay, I'll just yell. It's easier. If people are falling asleep, let me know. Let the speakers know so that we'll wake you up. Okay, so first couple of points. So there is handouts that you should get one of them. Mostly they are not the most up-to-date versions, but they are there. I mean, these are as of Saturdays, and then obviously we've been working really hard, changing everything. But you can at least write notes. I thought at least a version of it is useful than not having any. In particular, the most important omission is the beginning 5 slides or 6 slides, actually maybe 12 slides, would not be there because we were going back and forth on the overall overview of everything that we're doing. So that the final version of all the slides would obviously be available on the website. But once the detailed technical parts start, you have more or less the slides, so you can take notes of this. And the other thing, of course, is please stop us at any time if you have questions. We have a bunch of slides, but I think the world is not going to end if we don't complete all parts. It would certainly end if you don't get anything out of it. So it will be much more useful to stop and ask questions. Okay, that's the house rules part of it. So the tutorial is preferences and partial satisfaction in planning. What I'm going to do is spend, I think, about 10 minutes or so giving an overview of the overall tutorial, and then, and which part is being done by who. So actually, the 3 of us, Jay and Kore and myself, are going to split the actual speaking, with them really doing most of the technical parts. So anyway, so preferences and partial satisfaction planning. So for a few people, if there's anybody here who hasn't heard of what automated planning has been doing, this is just a single slide idea that you have some specification of actions in terms of their effects and preconditions, and then you have initial state and you have a goal state, and you're trying to find a string of these actions, search for a string of these actions that will get you to the goal state from the initial state. Okay, it's a deceptively simple problem, and in this particular scenario, you assume that everything is known about the initial state, all the action descriptions, the goals, and all the goals must be satisfied, and a plan is considered a plan only if it satisfies all the goals, and your job is to find one. Okay, and this been, that problem, of course, it turns out that you can write Tower of Hanoi in this formulation. And so just for that, you can see that you can have exponentially long plans, plans whose length is exponential in the input specification. So essentially, the problem itself becomes a pretty hard problem. It's a piece-based complete problem. And there's been a lot of work over the years. And the biggest change in planning community in the past decade or so is really the speed up in the ability to generate large, long plans in reasonable times. Okay, so here is like a little slide from, I guess, back in 1994, I think, by some planner, where basically you're comparing your performance with somebody else's performance, and of course, being a piece-based complete problem, all you can expect is some sort of an exponential, and you're just trying to reduce the growth rate, and so you get to make fun of the people whose growth rate is much worse than yours. Okay, so clearly, presumably, unless you're already fallen asleep, this graph was made by these people, not those people. Right. So that was good, and then of course what changed, of course, is this is actually about 3-4 years back, and I think it's even better now, of a similar curve, except in a much more complex domain with significantly large number of actions. So in fact, we can generate about 100 action plans depending on the domains in under seconds. Although if you heard some of the offline discussion that was going on before the tutorial started, you can also generate pathological problems that can put planners in deep trouble. Okay, but there are a reasonable number of interesting domains where you can generate large-scale plans quite fast. Okay, so and in fact, search control has really been the primary revolution in automated planning in the past decade. That's good. We could actually talk about what really was search control, what are those ideas, but that's not what this tutorial is about. So assuming that you can solve this problem fast enough, what should we be doing next? Okay, yes sir.
Well, is the primary state of the art using converting everything to Boolean satisfaction and solving that?
That was not actually, no, in fact, that's a good question. So in fact, there are multiple techniques here. So the ones that are winning the state-of-the-art performance are heuristic search planners. The conversion to SAT is good, but not the state-of-the-art. You know, it turns out, and of course there are multiple approaches. It's one of the competitive approaches. It hasn't completely fallen by the wayside. Right now, in fact, I tell my students that the second best way of solving any new planning problem is to compile it into SAT. Okay, it may well be the first best way if you don't want to spend any more time on finding more customized heuristics. Okay, but the answer to the question as to whether SAT solvers are winning the competitions, no, that's not right.
Interesting.
Heuristic search planners are winning the competitions. Okay, and in fact, one of the interesting things is as the tutorial goes on, you will hear for partial satisfaction planning too, you will hear approaches based on SAT solving, based on heuristic search, and so on. So it's not that we're just going to give you one single solution because we don't quite know, as to which one will win in the longer run. So we will give you a series of a variety of solutions, all of which are competitive. Yes.
Just to confirm my understanding, I guess part of the question whether one approach is better also depends on the optimality criteria. So suggestions might be better for stats solve if you try to minimize the extent, basically the number of parallel planning steps. If you really want to do sequential cost-control planning, maybe the research planner does have an advantage.
That's true, and yeah, that's true. So actually, I mean, that's a whole entire discussion, interesting discussion that we could have separately offline. But as I said, what I want to say is, if we are doing this fine, then what should we be doing next? And obviously, you should be extremely surprised to hear that what we should be doing next, as I'll tell you, is partial satisfaction planning. But before getting there, let me tell you what has been happening in the community. One direction that has actually been considered, and it's a pretty main direction, is the problem that I showed you in the beginning is what's called a classical planning problem, where you assume the initial state is known, the goal state is known, the goals are specified up front, and the actions are deterministic and they're instantaneous, and you're solving the problem there. And so now that we can actually solve those problems, then you can start considering maybe what if we have actions with durations, actions with costs, combine those, allow non-determinism, consider partial observability, consider stochastic dynamics, and this is a great direction for the community to improve on the speed ups that were made on search plan, on the classical planning. That is a great direction, and in fact we can have an entire set of tutorials on that. Now, and as I said, so that's basically starting from the classical planning assumptions, which are, as I said, static, deterministic, observable, instantaneous, and propositional. You can start relaxing each of those assumptions, and you will get a new planning problem. And as soon as you relax one of the assumptions, your speed up reduces drastically. But again, the more you actually, one of the interesting things that the community has found is that the work that went into classical planning problem has been quite helpful in designing effective solvers for all these other problems, stochastic solvers, stochastic planners, temporal planners, and so on. Some of the best stochastic planners now use deterministic planners as the basis to get the scale up. Okay, so that's one direction, but as I said, this has been one way the community has been proceeding. An orthogonal direction, which is really what we're going to talk about in this tutorial, is so in all these cases you're considering find a plan that satisfies my constraints, a plan, okay? But in many cases you have many plans, quote unquote plans for the problem. And the real issue becomes finding a plan of a right quality, of a reasonable quality. Okay. Since the planning problem has been hard enough, just satisficing approaches, that is finding a plan, was itself hard enough. But now that you can actually solve satisficing planning well enough, you can start thinking about what if in fact the users have a variety of quality metrics on the plans. And for example, there are entire areas such as if you do query optimization in databases, there, finding a plan is easy. Finding the optimal plan is really the most important thing. Okay, so you could start talking about what kinds of quality constraints are required by the user, and to support that, how hard would it be to support the different kinds of quality constraints on the planning. So this will actually open up a sort of a different direction. Okay. Now the interesting thing, the reason I put this as orthogonal is that you can situate yourself in deterministic planning, which is more or less what we will do in this tutorial, and start talking about how to allow a variety of rich types of quality constraints. And having heard this tutorial, you can then also ask yourself, I could do the same kind of direction, but for temporal planning or for stochastic planning, and so on. Okay, so it really is an orthogonal direction of attack. And so that's what, and clearly there are a variety of planning applications which require, quality constraints have to be satisfied. It's not just enough to say the goals are satisfied. It's like there are many plans that reach the goals, but there are a variety of constraints that the user might have. And in fact, one of the interesting things is even when benchmarks were allowed for automated planning competitions, like there is a biannual international planning competition where people have made benchmarks that classical planners, for example, would work with, or stochastic planners would work with. Many of these benchmarks originally were made and were meant to be quality aware planning problems, but then when the actual benchmark was made, that quality constraints were thrown out originally. So in fact, I was just talking to David Smith, who was one of the guys who came up with this thing called satellite domain, and then people obviously simplified it such that the quality constraints are thrown out and all you need is to just reach the goal. So again, the point is, it should not be surprising at all that you might need a variety of preferences and quality constraints to be satisfied in addition to just reaching the goals. And so that's what we will be focusing on in this tutorial. Okay, and so this slide hopefully is like the most important slide I get to talk about, and so let's pay some attention to this in terms of what are the dimensions in which the variety of approaches for this, what I said, partial satisfaction or preferences in planning, those approaches, how do they differ? Okay, and there are two axes that you want to think about. One axis is, if you have preferences, if you, the user, have preferences on the plans, on what aspects of the plan do you have preferences on? Okay, so for that I would consider at least three parts. One is, you might have preferences on goals. You have a variety of goals that need to be satisfied by the end of the day, but some are more important to you than others. So all your preferences are on the goals. Now even if I just have preferences on the goals, it turns out that things can be complex. I mean, suppose I have goals G1 to G20. I might say, well, remember that in a classical planning scenario, G1 to G20 all must be satisfied. If you fail in any one of them, the plan doesn't work. Okay. Now, if I start having preferences, I get to say G1 is 10 units good for me. G2 is only 7 units. So if you have to pick between G1 and G2, maybe you'll pick G1. Okay. Furthermore, actually, your preferences on goals might themselves have interactions. So for example, you might say, if you just achieve G1, you get 10 units reward. If you just achieve G2, you get 17 units reward. If you achieve G1 and G2, you might get a reward, not 17, but sometimes less than 17, which is, for example, G1 is one car, G2 is another car. If you have two cars, it becomes more of a headache. Okay, and so you don't get as much, you don't get additive utility. And similarly, you can also get G1 plus G2 is greater than, so the G1 and G2 together, reward could be greater than G1 plus G2. So for example, if I have right shoe, I get like a cent, left shoe, a cent, and if I get both, hopefully, it's like a Visa commercial. It's much more useful to have both shoes. Okay, so there, in terms of preferences on the goals, you might even have the ability to talk about interactions between the rewards for the goals. Okay, that's one type of preferences. And even as I'm talking about this, you might be thinking in the background, you need languages to express these preferences. And not surprisingly, that's some of the stuff that we'll be talking about. Okay, if This goals is basically what happens at the end of the day. When the plan is complete, then I have preferences. But many a time I actually have preferences on the sequence of states through which the plan goes through, the agent goes through. Okay? So it's not just enough for you to drive from here to, like if you're like a bus driver, it's not enough for you to just get fastest, route to go to some place. If you are going very close to the end of a precipice, then, your boss, they have these things right in the back of the buses saying, if you don't like my driving, call my boss. And then, you will call the boss and say, this guy is going too close to the precipice. Why? Because the sequence of states through which the plan is going through, they are not desirable. Okay? So you might, for example, in fact, many international flights, for example, have this restriction that at no point of time should you be more than about like half an hour away from the closest airstrip. That's why passenger flights take certain paths so that they, if there is any problem, they'll always have some airstrip to get to. Okay? So again, you might have preferences on the state sequences, of which, of course, the last state is one state. Okay? So in some sense, the preferences on this is more general than just preferences on the goals. Okay? And then what's the last thing that I want you to think about is preferences on the plans themselves. Okay? So if you do a plan goes through states, but it also uses specific actions to go through states. And people might have preferences on the what actions are used to go through the states. Okay? So you can have preferences also on the plans. And those are at least these three things you can think about. And on the other axis, if I do have a preference, how do I evaluate that preference? If you give me a plan, and if the preference is satisfied or not satisfied, how am I going to ding you? Is this going to be qualitative or quantitative? So a qualitative basically means I'm just telling you what the preferences are. I'm not giving any numbers with respect to the penalties associated with them. Quantitative means I'm also providing numbers in terms of rewards and penalties for those preferences. Okay, so now you have a nice little two-dimensional space, and you can pretty much talk about approaches for partial satisfaction and preference-based planning fall as points in the spectrum. Okay, and so I'll talk to you about a couple of things, and in fact that's what this tutorial is going to be about. One specific thing is if all your preferences are only on the goals, and the preferences are quantitative, which is in some sense the first example I talked about, where you have a reward associated with goal 1, a reward associated with goal 2, and then you may have a different reward associated with goal 1 plus goal 2. Okay? Those kinds of preferences, if you are expressing those preferences and supporting planning with respect to those preferences, that problem has been sort of called net benefit problem. And there's a significant amount of work that's been done on that. So in fact, the first part of the tutorial actually would be about that problem and the different approaches for that problem. Okay? Now, one of the interesting things in the net benefit problem is you have to think about the utility, the rewards for the goals and the costs for the actions. The question is whether the costs and rewards are in the same currency or are they in the different currencies. The simplest assumption is to assume that they are in the same currency, in which case you just take the net benefit, which is the cumulative reward minus cumulative cost. Okay, if sometimes the costs are actually in a different units, then you ultimately have to say, find me the highest reward plan subject to the following cost constraints. So get me the plan with the highest reward subject to the fact that I only have 20 minutes to complete the planning, to plan execution, and I only have 18 gallons of fuel. Okay, and that aspect, that's actually a subclass of the net benefit problem called the resource constraint net benefit problem, and we'll also talk a little bit about that. Okay, so that's one part, and as I said, we'll talk spend a bunch of time on that. And then there has been some work on having preferences on goals, but those preferences are qualitative. And that would be, for example, an example planner here is pref plan, and then we'll talk about that. And then on the state sequences, if you are supporting preference on the state sequences, those are called trajectory constraints. There are a variety of planners that support trajectory constraints in the quantitative setting. Remember again that to some extent, if you say you have the world's best planner for this, it should actually be supporting this because it's more general. Okay? And then similarly, you could have trajectory constraints and qualitative preferences. Okay, that's LPP model. Again, there are a bunch of names coming up. hopefully, as the tutorial goes, basically this is also explaining to you the overview of the pieces that we'll be talking about. So in a minute, I'll actually tell you which pieces talk about which, but then here is an LPP which talks about state sequences and qualitative preferences. If you have preferences and plans, there is a way of doing it. It's not the only way, but one idea is to have HTN, hierarchical task networks, to say that the final plan should be parsable by these hierarchical task reductions. Okay? And that's called HTN preferences. And then there hasn't really been that much work on quantitative version of that, but we might actually talk about some ideas where when you're learning these preferences, you might wind up having what's called a PHTN preferences, which tell you what is the level of preference for each of these HTN schemas. Okay, so that's the kind of a dimensions of variation. And the second slide that I want you to think about is what are the challenges in generating planners for these variety of places. Okay, one of course is the representation. You need to have a language for representing preferences, and you should also be thinking about, if I have preferences in one type, can I compile them down to another type? In which case, then you don't have to keep writing new planners for each set of preference constraints. Of course, we'll be thinking about synthesis. You should be able to evaluate the plan quality. You should be able to synthesize plans with higher quality. And can you use the existing heuristics? For example, as I mentioned earlier, heuristic search planning has been one of the more effective approaches for classical planning. Can you change those heuristics such that they can support a variety of preferences? Okay. And one of the other interesting things that we'll spend some time but not as much is, if I give you a bunch of goals and all of them are satisfied, it's one thing. But if some of them are not satisfied, whoever came up with those goals, they will feel left out, and they would like to know, how come, why me? That's the biggest question. Anytime anything bad happens to you, you say, why me? Oh God, why not my friend? And you need an explanation, right? So the planner, God doesn't have to explain, but the planner agent has to explain. Because, following reason. So there should be some way of explaining planners' decisions as to why a certain set of objectives were picked as against others. And then finally, one of the things is, in these two, we are assuming that preferences and complex languages are specified upfront by the users. What if users have preferences but are not articulate enough to write these preferences in these languages? Okay? And what if the preferences are incompletely specified? What can you do when preferences are incompletely specified? And there the challenges would be, what does it even mean to come up with solutions when the preferences are incomplete? Okay? And to have a feel for that, I ask you to think about what would happen if you called a human travel agent and said, I want to go from my place to Atlanta, and they said, here is the ticket for you. You get mad at them because you say, how dare you assume what is the best plan for me? You should talk to me for some more time. Give me a couple of options. Even when my kid was small, I would ask him, what would you like to have for dinner? He'll say, what are the choices? He doesn't want to tell me right away. Give me the choices. So you need to be able to generate options when you have preference incompleteness, so that in picking the options, the user is in some sense able to express more information about their implicit preferences. And then finally, that could lead into learning of the preferences itself. You may be able to use this interaction to learn the preferences, which then can be used next time around, in the approaches that we do. Okay, so that's basically, so the dimensions of the dimensions of variation as well as the challenges sort of gives you an overview of the tutorial. That this itself is the outline for the tutorial. First, Jay will be talking for a long time about, before the break, about planning for net benefit. And then Jorge will be talking about trajectory constraints and preferences, qualitative preferences, HTN planning with preferences. And then, time permitting, and if you don't ask any questions to them at all, and I actually hope you ask questions so that I don't have to do this. But, if we wind up having more time, we will talk about handling partial and unknown preferences. Feel free to ask questions. It's not just so much that I don't need to talk in the end, but I really think it'll be better if we get something out of it rather than, we get through all our slides. Again, this is just like a linear outline. If I put this in the dimensions of variation, really, the net benefit problem, which basically is preferences on goals, and they're specified with quantitative evaluation matrix. That's the net benefit problem. Jay will be talking a lot about that. And then Jorge will basically look at HTN. In fact, our order would be trajectory constraints, qualitative preferences on goals, qualitative preferences on the state sequences, and HTN preferences. So Jorge is doing all of them, and he speaks extremely fast. So that's okay. And if we do all that, then we will talk about this last part. In the third part, I'll get back and talk about what to do when we have incomplete disparate preferences, and how do we handle them, how to learn certain classes of preferences. Yes.
Do you have any easy explanation for the difference between optimal and Pareto optimal?
So Pareto optimal essentially. So again, if you have multiple objectives about the plan, so it's like travel planning is a classic case. So all of us want to get to the destination with the cheapest fare and at the shortest, and also the shortest amount of time spent, unless you have a thing for airlines and want to hang around in the airlines, right? So, but now how much is an extra hour in terms of fare decrease? How that we don't know, and obviously for Bill Gates, an extra hour is just too much. So he's willing to pay $1 million to get his own private plane so that he can cut the extra hour. My graduate students tend to say it doesn't matter if you can save $2. We don't mind hanging around in the airport for 2 days. Okay, right? So the point, of course, is so you have two dimensions now. The travel cost and the travel duration and the price, okay? And all you know, in this case, all you know is if I give you a plan which takes, $200 to go from Phoenix to Atlanta and takes 2 hours, and takes 4 hours, and another plan which takes $300 to come from Phoenix to Atlanta and takes 8 hours. Most of you would know that the second plan is useless. Why? It's because Pareto dominated. It's dominated by the other plan. It's dominated in all the directions. If I have two plans such that one is not dominating the other, then they are essentially Pareto incompatible. And the Pareto set is the best plans that are not dominated by each other. And the specific user might know which plan they want among the Pareto set. So you never want to tell your users dominated plans. Okay, whenever you have multiple objectives, essentially you have many plans that could be potentially good for you. The only things that an automated planner can do is not give you completely useless plans where the second plan is worse both in terms of time and cost, for example. Okay. This actually, if we survive until the end of the tutorial, I'll have some time to talk about Pareto sets, because when you have incompletely specified preferences, this is exactly what happens. A normal optimization problem again becomes a multi-objective optimization problem just because you don't have full preferences available. And so you actually present the user a set of travel plans and let them pick. And then from that you can learn how they are combining the time and the cost. Okay, so that's basically what we're going to do. And as I said, the tutorial outline is that Jay is going to start talking about planning for net benefit.
So the story of net benefit really starts with sort of classical planning. And here's the taxonomy of exactly how you might think of how the net benefit problem might come into existence. So the first problem that we have is the classical planning problem, where you're just trying to find plan existence. You're just trying to find whether a plan exists or not. And you can sort of think of, well, a couple of optimization criteria. One is that you want to have maybe the shortest length plan. So that is another one idea for perhaps an optimization criteria over plan existence. But you can also think about having costs on the plan. So you actually have costs on actions, and you want to find the minimum cost plan. But then you might also be thinking about whether you want to satisfy all the goals or not, and that's where partial satisfaction planning comes in. So one idea, and it's kind of the easiest idea, is if you have just a huge set of goals and you only want to satisfy some of them, you might want to think of just satisfying the maximum number of those goals. So that's where we get PSP goal. You could also consider perhaps combining plan length and goal, so you would get this thing, and this is where you might think of proto-optimality, where you have two you have two objectives, one on the number of goals and another on the actual plan length. But we can also think about adding reward to goals, and that's where PSP utility comes in. So you just want to satisfy the set of goals that give you the most reward. So you give a reward to each goal, and you want to satisfy the goals that give you the maximum reward. Well, you could, and this is where PSP net benefit finally comes, is where if you want to combine plan cost and plan utility, so that you want to get the best net benefit, that is the best plan with the difference between reward and cost being at maximum. Of course, you can also combine these more like you did with PSP goal length, and you could have these two optimization criteria where you would have utility and cost separate, but you just want to, but if you have that case, then you have to kind of present a huge set of plans rather than a single plan. So what we're going to focus on, and what most people think of, is PSP net benefit. And this was actually in the International Planning Competition. There was a track on PSP net benefit in 2008. And I'll go over some of the planners that actually did PSP net benefit, both from the competition and planners that came before the competition. So to be a little more formal about what PSP net benefit is, if you have a PSP planning instance, you have a set of states, and you start with an initial state, you have a set of operators. So in planning, the idea is that you want to get from the initial state using the set of operators to a set of goal states, or to a goal state that's in the set of goal states. And what we do is we can assign a reward function over the set of goal states. So each goal state can give any reward, and you can define this function any way you want. So you could either define it such that every single individual goal gives you reward, or you can define it such that combinations of goals will give you different rewards than perhaps the sum of the rewards of each goal. You could also consider adding penalties, and I'll talk about that a little bit. But again, the optimization criteria here is that we want to satisfy the reward minus the cost to its maximum. So we want to get the maximum reward minus cost. And so again, our reward function can be anything. So you could even imagine, rather than just having reward on goals, you could also imagine putting penalties for not satisfying goals. So if a goal doesn't happen in your state, then you might want to actually penalize the state such that you get less total net benefit. So your reward function can actually also incur cost if a particular goal doesn't have reward, and or a particular goal doesn't exist in the state. So one example of this is, for instance, hard goals. You could define hard goals such you give infinite penalty if you don't actually satisfy the goal. So if you maybe just have a hard goal that you want to reach the end of a hallway, something to that effect, then you can but there's also reward on reaching the end of the hallway. You can give reward for reaching the end of the hallway, but if you don't satisfy that, you actually get infinite penalty. So it factors into the calculation of net benefit. And another thing to consider is, I think Rao kind of went over this a little bit, is if you have a fixed resource, so if you say you have fixed amount of time or fixed cost, you might want to try to find the best net benefit plan within just that fixed cost. So if you have a fixed amount of fuel or a fixed amount of money, you might, within those constraints, you might want to find the best net benefit plan. So I kind of already went over this, but there's two real things that you have to consider when you're thinking about net benefit planning problems. The first is whether there are cost dependencies that come from the plan. So an example of a cost dependency is that if on the way to delivering coffee to your boss, you can also stop and deliver papers to your coworker, then there's a cost dependency there because you're actually spending costs on your way to your boss, but rather if you look at each individual path separately, then you don't actually get the sum of the cost to reach your coworker plus the cost to reach your boss. What it is is you're sharing an action here. You're sharing an action to go from wherever you are to the front of the door to your coworker, and that action is shared between both reaching your boss and reaching your coworker. So that's an example of cost dependency. And these come directly from the plan, whereas reward dependencies, utility dependencies, come from the user. So these are things that are specified by an actual human being. So the example here is that if I have socks and shoes, then if I just have socks, then I get a reward of 20. If I just have shoes, I get a reward of 50. But if I have both, then I don't get the sum of the rewards. I actually get 300, because having both gives me 230 altogether, and then I could sum up all of these rewards and finally get a reward of 300. So it's important to realize that reward dependencies come from the user, whereas cost dependencies come from the plan. So the question comes up is, why is this a hard problem? And it really comes from the fact that we have a set of goals, and we need to consider which set of goals we need to choose. So in this example, a student is trying to get to a conference, and there's a 6,000 reward for getting to the conference. And if the student visits this luxurious park on the way, there's a reward of 600, just a small reward for having a little bit of fun. Well, so if the cost to traverse to the luxurious park is 3,500 and the cost from the luxurious park to the conference is 2,000, you see that this sum, 3,500 plus 2,000, is bigger than the cost to just go directly to the conference, which is 4,500. So the question is, which should the student do? Should the student actually get to the conference via the park and get a little reward there, or should the student just go directly to the conference? And it turns out that if you look at each individual set of goals, and these are just 4 goals, in order to find out which is the best set, you really have to find the plan for each of these possibilities. So if we get goal 1, goal 2, goal 1 being the student at the conference, goal 2 being the student at the luxurious park, then we get a total net benefit of 1,100. If we just satisfy goal 1, which is going just to the conference, we get a total net benefit of 1,500. And if we try to do just going to the luxurious park, which I'm sure every student wants to do, but it's a very bad idea, because they'll get a negative reward, so they'll actually incur cost. And so we have to actually go through each of these possibilities in order to really find out what the best combination is. And this is very impractical in general. If we have a lot of locations that we want to visit, then trying to find a plan for each of these combinations is quite impractical. We have to go through 2 to the n goal combinations in order to really find which is the best. So, how have these things been defined? Well, so in the planning competition, there was introduced a planning domain description. The planning domain description language is used as the standard for defining planning problems. And it turned out that in 2006, the people who ran the competition decided to add something called simple preferences. They're not quite net benefit. What they are is that if you don't achieve a goal, then you incur penalty, and that's it. It doesn't have any reward explicitly defined for actually getting reward for achieving a goal, just penalty for not achieving a goal. And it turns out, though, that you can compile this kind of preference into a net benefit planning problem. And so one of the guys who created the domains, Patrick Haslam, figured out a way to do this. And so one of the domains in the 2006 planning competition actually ended up being a net benefit planning problem. That was the Rovers domain, which is sort of the classic, net benefit planning problem. And then after that was figured out, then what they did is they had a complete net benefit planning track in 2008. So the 2008 planning composition ended up having an optimal net benefit planning track, but not a satisfying net benefit planning track, because there just weren't enough competitors for the satisfying track. I think there was only one competitor. So just really quickly, how the simple preferences can be defined as net benefit is, so you have some cost here. So this is stack cost for stacking products on one another in the OpenStax domain. And so you get some stack cost for here, so that's pretty easy. You just add the stack cost to the total cost on the action, and then you can define soft goals by just saying that they're a preference. So in this case, you've delivered O1, that's order 1, which is product 1 is part of order 1. So you've delivered product 1, which is part of order 1. And again, you've delivered product 2, which is part of order 1. And then you put a violation cost, and this violation cost ends up being equivalent to the reward of actually achieving the goal. And the way you convert this violation cost into reward is you have the sum of all of the rewards, and you use that as your as something you're actually subtracting from. So basically, you're trying to maximize your net benefit. So you have your total reward that you can get minus all of the things that you don't actually have, and that gives you your actual reward, and then you add that to your total cost. So how are these things solved? That's the big question. And there have been many different thoughts on how to solve this problem. So sort of the easiest thing to think of is, if any of you are familiar with MDPs, since we have rewards and we have costs, the easiest thing to think of is to perhaps encode these net benefit problems as MDPs. And this turns out to be a possible solution, and you can actually get optimal plans from it. Another possibility is, since we have numbers and we're trying to, we have an objective function, you may think to encode the problem as an integer program, an IP, and you can do this, and you get bounded suboptimal. You get a bounded suboptimal solution. The unfortunate thing about IP is that you can only solve the problem up to some bound. That is plan length. And then you could do something similar with using maxsat. So this is the sort of classical way of trying to solve plans optimally. A lot of people have tried to use SAT to solve problems optimally, and so people use maxsat, and this just happened this year actually. Someone tried to use maxsat to do bounded optimal planning for net benefit. And finally, what has usually worked in the past the best in terms of scalability is heuristic search. And so there are a ton of people who have actually applied heuristic search to solve the net benefit planning problem. And so these are really listed in order of scalability. So the most scalable, it tends to be heuristic search. The least scalable is MDP formulations for net benefit. So the MDP formulation, just to go over the worst possibility to see how this kind of works, is that you might think sort of the easy thing to do would be to just encode for every state that has all of the goals, has some subset of the goals, you want to put some reward on that state. And then you could just have every state that has all the goals have this reward, and then you just can solve the MDP. And it turns out that that's not the best idea, because if you achieve goal G1, as you go on to try to achieve goal G2, every single goal from G1 to G2, or every single state from G1 to G2 could be another goal state, because it likely has G1 in it. So you actually accumulate your reward as you go from G1, the state with G1, to the state with G1 and G2. A better idea is to actually have a proposition called done, which essentially corners off all of the goal states. So what this means is that you only are able to begin achieving goal states after you are completely finished with the planning problem. So what this does is this allows you to think of evaluation actions essentially, that can only run after you've reached into this goal, this goal space, this done space. And so what you do is you have an action called maybe finish that gives you this effect called done, and you then after you're done, then you have actions with a precondition of done that evaluate and give you the actual goals, evaluate the set of goals that you have in your state. And so you could find with this method an optimal policy, but it tends to scale very poorly, and much more poorly than heuristic methods, and quite a bit more poorly too than IP and MaxSat methods.
Question?
Yeah.
So when you say scales poorly, there are a lot of techniques that use heuristic search for MDPs. So do those scale as poorly as well, or are you talking about standard value iteration and policy iteration over the whole state space?
I know that the SPUD solver was used when this was done, and I'm actually not familiar to know exactly what that is.
Yeah, so SPUD solver doesn't have any reachability or heuristic guided search.
Okay, so it could be that, maybe someone could try it. Okay, so another optimization method that people use, another method people use to encode net benefit is to use integer programming. And integer programming encoding, it tends to be much more straightforward, at least in theory, because you don't have to deal with this done space. You don't have this accumulation of value. It's just whether you have the action or not. If you have the action, then you incur some cost. If you don't have the action, then you don't incur the cost for the action, of course. And if you have the goal, then you get some reward. And if you don't have the goal, you get no reward. So basically, the encoding is pretty straightforward. We take the planning graph, and we can encode the planning graph as an IP. And I'll go over the planning graph in a little bit, but basically it's a multi-layered structure that allows you to look at the causation of actions to propositions. At any rate, you encode the planning graph, and you use binary variables, so whether you have an action or not. If all of the actions conditions are satisfied, then you require that the action is actually in the plan. Or you could require that the action is in the plan, so it's enabled or not enabled. And if an action gives a proposition, then you require that that proposition is in the plan. And finally, you have, if a proposition is in the initial state, then you assign it the value of 1. And so this kind of propagates through the IP solving process. And for regular classical planning, you just want to minimize the number of actions that you have. But all you do if you are going to do net benefit is you change the optimization function so that now you're maximizing the reward minus the cost. And this is bounded length optimal because the planning graph encodings are actually, you can only find the optimal solution up to some length k. And you can continually grow k as long as you want, but you can never guarantee that you're actually going to get the optimal solution until you bring k up essentially to infinity. And another method that people have used is weighted MaxSats, and this is very recent work. It just happened at ICAPS this year. Essentially, again, you encode a planning graph, but this time as a SAT, and the slight difference between IP and weighted MaxSat is that weighted MaxSat really likes minimizing things. So you just need to convert the maximization function that you have for reward to a minimization function, and you do this using a similar compilation as you do for net benefit to simple preferences from PDDL3 to net benefit. It's a very similar change. So you're now but now you're minimizing your basically your cost, and this actually beats the IP approach, which is interesting, and it's interesting that no one tried it until this year, but it actually does beat the IP approach, but again, it's a bounded length optimal approach, so you aren't going to necessarily get the very optimal solution. You'll get a bounded length optimal solution up to some k. So I've talked about these that tend to be okay, but they don't scale very well. They give lots of nice optimality guarantees, but they scale pretty poorly, it turns out. So the big problem with these is that they don't scale as well as modern heuristic planners. So the question is, of course, whether we can leverage our current technologies for classical planning into the space of net benefit. So can we take our state-of-the-art planner like FF or Fast Downward and actually do something that might allow us to solve net benefit problems to high quality? So this is a diagram of how you might decide, using the current methods, exactly how you might use a modern heuristic planner. So you start with a net benefit planning problem, and you decide whether you want to select goals or not. And what I mean by select goals is if you want to actually select a set of goals up front and then try to just solve a planning problem, a regular hard goal, classical planning problem using that set of goals. So this is selecting a set of hard goals, or selecting a set from the set of soft goals in your net benefit planning problem and turning them into a hard goal, and then running a cost-based classical planner from there. You can also consider, rather than just selecting goals up front and just running a classical planner on them, you could also consider compiling the goals into some other form that actually gives you a cost-based problem, and then you could again use your cost-based classical planners. But if you don't choose to do either of those, your only choice is to take the original net benefit planning problem that you have and actually try to solve it directly using some specialized planner that works specially for net benefit. So this is the planning problem that's kind of going to be the example, variations of this for at least part of this net benefit discussion. And this is the rover's problem. So you have a set of locations, alpha, beta, gamma, and each of these has an experiment that you want to perform. And this at alpha, you want to take a soil sample. At beta, you want to drill some rock. And at gamma, you want to take a picture. And each of those has some reward. So having the soil will give you 20 reward, having the rock will give you 50 reward, and having the image will give you 30 reward. So say these just come from a scientist who decides this is the priority that she wants to give. And then each of these has costs, and these costs will change throughout the various examples. Each of these edges moving between each location, and actually taking the samples has some cost too. So I promised a little overview of the planning graph, so I'm going to give a quick overview of what the planning graph looks like for this problem. This is actually what's called the relaxed planning graph, which means it ignores delete relaxations. And that's a common heuristic that's used in automated planning, is to create a version of the problem that ignores deletes on the actions, and then solves that problem as best as possible. So it turns out to be a polynomial time operation to solve a problem that ignores delete effects. So here are some action costs on each of these actions. The way the planning graph works is that we start with our initial state. We apply all of the actions that are applicable at that initial state. So we look at, this is the proposition layer, this is an action layer. On the action layer, it contains all of the actions that are applicable at this state. After we apply those, we get a set of propositions, a new set of propositions. We propagate the proposition from the initial state, and then we have a set of propositions that are given by the effects of the actions at the previous layer, and then so on. We do the same thing with this new proposition layer. We take all of the actions that are applicable here, and we follow through in this way until we get a end sort of state, an end layer that has all the goals inside of it. And this is sort of propagating, you can think of this as propagating the causal relationships between the propositions and the actions. But you could also propagate costs, and this is important for when we're actually trying to select goals up front. If we're trying to select goals from the onset, and we kind of want an estimate of exactly what the cost of reaching each of these goals will be. And so we can propagate, while we're propagating each of these actions and the propositions, we can also propagate costs over this. And so taking a sample costs 20, so the cost of actually having the sample, you can say, is 20. And then we can do this same thing. Here's where the other goals are. We've propagated the cost for sampling a rock to this goal, having the image of 35. And what this is it's the sum of actually having the rock. It turns out that having the rock available, let's see, so being at beta, where the rock is, has a cost of 10. You sum the cost of being at beta plus the actual cost of the sample to get the cost of the action sample rock at this layer, at this state. And then that is reflected finally in the final goal. So these are the approaches I'm going to talk about in terms of using cost-based classical planners. Alt-PS was, and the orienteering approach from David Smith were the two of the first that tried this method. Alt-PS uses this planning graph structure directly to select the goals up front. And Smith's orienteering approach, that also uses the planning graph, but it also, on top of that, uses what's called the orienteering problem, which is a variation of the traveling salesman problem. And then there's another orienteering approach that's a little more recent, where they're trying to actually take, rather than, so Smith's orienteering approach looks at each individual goal, and this orienteering approach actually takes pairs of goals. So it's just another way, and I actually won't go over this one, but I'll go over the first two. And then the other method that I'll talk about is simply compiling the problem from a PSP problem, a net benefit problem, to a cost-based problem. And this is actually, turns out to be very similar to the MDP compilation that was done, in which you have this done space that I talked about earlier. But at any rate, this is something that came out in 2007, and then there was a recent journal paper in a research note in 2009. So Alt-PS, again, this is the same planning graph that we saw before. Its approach, it selects a single goal, it extracts a relaxed plan for that goal. It selects the next goal that has the best next net benefit. So it takes the net benefit of the first goal. So in this case, it chose sort of at random the goal have soil. And then it takes the net benefit of just having that goal by itself. And that turns out to be 50. And then it goes on and tries to select the rest of the goals. And I think, yeah, great. I have an example here where here's all of my choices. Have rock, or have soil, have rock, have image. You choose, you extract a relaxed plan for each of these goals individually. And then you look at the net benefit given the relaxed plan. So relaxed plan, again, is a plan over the relaxed problem of ignoring delete lists. So you extract a relaxed plan from the planning graph. And you look at the value you get for net benefit for each individual goal. And then you choose the one that gives you the highest. So this is a greedy approach. Then you take, then you look at adding the various other goals. So you look at adding maybe have rock, and you extract a relaxed plan biased by your previous relaxed plan that you have. And then you get a net benefit value for that relaxed plan, and you do again for each goal. You extract a relaxed plan again with these pairs of goals. This is have soil, have rock. Gives you a net benefit of 45. And have soil, have image gives you a net benefit of 10. So it's the case that we look at have rock. So from have soil, have rock, we extract another relaxed plan that is again biased by our relaxed plan for have soil, have rock. And then we get a final relaxed plan where we have all three goals. This turns out to be a bad goal choice compared to just have soil, have rock, because it gives you less net benefit. So you choose to have soil, have rock. So the question is, does this approach work? Does greedily sampling from a planning graph like this actually do well? And the problem is that you could easily imagine that you could choose goals that end up being mutually exclusive from one another. So if you have maybe rock is on the top of the hill and soil is at the bottom of the hill, you need to traverse down to the bottom of the hill. It could be that you could, and you can't traverse up the hill, for instance. You can only go down. It could be that for some reason it costs more to it looks like it costs more to actually take the soil. So you go down and you take the rock. But it turns out that you've chosen, actually this is not a good example, sorry. But basically the idea is that if you have mutually exclusive goals, you can easily choose them because you're not keeping track of your mutual exclusion. So you can easily choose two goals that you can't achieve together. So another issue is that you could end up choosing goals that actually give you low quality plans because this is a approximation method, a greedy approach. So one solution to the problem of choosing perhaps two goals that are mutually exclusive from one another is you can actually try to do some mutual exclusion analysis over the planning graph. And it turns out that there are already methods for propagating mutual exclusions over the planning graph. And so you can actually use these methods to propagate the mutual exclusions over the planning graph and try to find goals that actually have fewer mutual exclusions among each other in terms of the relaxed plans that they give. And what this will do is it'll add a penalty cost to goals that have more mutual exclusions than other goals. So, yeah.
It seems to me that basically there are two components to this approach. And so the first is kind of a hill climbing over the sort of goals you want, as the second is how you estimate the cost of achieving those goals.
Yeah.
And I mean, you can use any type of heuristic for estimating the cost, or you might even call a cheap satisficing planner.
Well, what do you mean by cheap satisficing planner? Because you would need to then, if you do that approach, and actually that has been tried, you would have to choose every single subset of goals and actually
so you're still doing hill climbing over sets of goals, but instead of using the relaxed planning graph to estimate the cost, you actually find a plan that achieves those goals. I mean, with classical planners now.
Oh, I see. So you're saying have one goal and then choose another goal, but you would Yeah. So basically, you could cut down the set that you need to consider in that way, and still do a greedy hill climbing approach. Exactly. Yeah, that's true. And that's actually kind of what I'll go over HSP-OP, which is Patrick Hoslam's planner. He kind of does something like that, but it's a good point. So, at any rate, these mutual exclusions between okay, so you can find mutual exclusions between actions and then propagate the mutual exclusions between the actions to goal sets, to propositions. And you can continue to propagate these mutual exclusions these monotonically decrease because as you actually go further and further down the planning graph, it turns out that you can do more and more in a non-mutually exclusive way. So what this does is it gives you a penalty if you have a mutual exclusions between, in this case, have soil, have rock. You actually get a penalty cost based upon the highest cost sub-goal through the relaxed plan extraction. So if you were to extract have soil, have rock, then the highest cost sub-goal that is mutually exclusive between the two subplans for have soil, have rock is 20, have soil. Okay. So another approach that's been tried is using the orienteering problem, and this is something that David Smith came up with. And the orienteering problem is a variation of TSP, where you have rewards that are given at each location, and you have a limited amount of resource, like gas, that you have to spend. And the idea is to maximize your reward given your limited gas resource. This approach, as you can see, it looks like a transportation sort of domain, and so this approach tends to be very good for transportation sort of domains like rovers, where you have a rover that needs to traverse through various locations, trucks, logistics, anything where you have this sort of single object that needs to traverse to several locations. And so the basic idea of it is that you do a cost propagation first for each goal that's at each location, and then you use and this is over the planning graph, and then you use the orienteering graph to try to solve for the whether you can actually achieve the goals together. And I'll go over an example of this. And then you solve the orienteering problem for what the goal ordering, as well as the whether you can actually achieve the goals. Oh, actually, sorry, I don't have an example. But so the idea, though, is that you take the critical set of the basis set, which is the critical set of propositions that you want to create locations out of. So you want to actually create locations in the orienteering problem. And the question is, what do you use to create locations? And if anyone's familiar with domain transition graphs from the planar fast downward, this is sort of what we're doing here. So we analyze the planning graph to try to find the best basis set by taking a relaxed plan extraction for each proposition, and then deciding how from the relaxed plan extraction how the proposition changes. So if it goes from positive to negative, then you know that it's probably a good candidate for a part of being part of the basis set. And then you take this basis set and you create this a state transition graph, which is basically like a domain transition graph, and project this basis set onto this orienteering graph, your graph G. Based on solving the orienteering problem, you can select the most beneficial goal, so the subset that looks the most beneficial given the solution to the orienteering problem, and then you figure out the order in which S needs to be achieved by the order in which you decide to visit each location in the orienteering problem. So these approaches, the question is, again, whether these will really work in general. And it turns out it's very easy to have n-ary mutex goals in non-transportation domains. And just a very easy example, if any of you are familiar with the blocks world domain, if you have if you have goals like this, where you want to have a block A on block B on block C on block A, you can see that this is actually, if you have all these together, it's impossible to have all those together. These are ternary mutex with one another, and it's actually turns out that alt-walt will end up selecting all of these, thinking that they're all alt-walt is the version of alt-alt that uses mutexes. It turns out that alt-walt will select all of these, and it will say there's no plan, it's not possible to solve this net benefit planning problem. And although I didn't try it by hand, I tried the orienteering planner, and it looks like the same kind of thing would happen with the orienteering planner. So this is goes to Erez's point. You can do something like a hill climbing approach, but except for solving for various sets of goals. What the HSP star P planner does, this is a planner that also selects a set of goals up front. It takes the reward of every set, which is very easy to calculate, and then it extracts it uses its propagation on the planning graph to decide which of these has the highest net benefit. So this is an estimated cost. This is the exact reward for each subset, and then it takes a net benefit of these and finds the set with the highest net benefit. So in this case, the first thing it would try would be soil rock. And then as it was planning, it goes through an IDA star search. So it goes through one single iteration of search up to some depth and some net benefit depth. And it then, if it decides that the actual cost is going to be too high, so if this changes to something lower than 30, so if it changes to, say, 25, then it will switch to one of these sets. It will switch to just soil or switch to having soil rock image. So it actually changes the set based upon how things are looking for this search. It keeps also, of course, the partial search through a transportation table that it's already done for this goal set, just in case it has to again go back and try this other goal set again, because now these start looking worse than 25, which soil rock would have been. And it turns out that this is actually an optimal approach, a fully optimal approach, and it just happens to do okay. It doesn't win the competition, but it turns out to be not necessarily a bad approach. So now that I've talked about selecting goals up front, I'll talk about a compilation from net benefit to cost planning. And the first step, you might think of creating a cost-based planning problem from a net benefit planning problem. I have a set of goals. I want to have a set of hard goals. Because I have a cost-based planning problem, and cost-based planning problems require hard goals. So sort of the easy thing to do is just create a set of hard goals from your set of soft goals. So I create a set of hard goals. I just put a prime by them. Now they're different. And the question is, now what do you do? Well, you have to consider, when do I want to actually achieve the hard goal? It's when I have the soft goal. So I create new actions that actually achieve the the hard goal when I have the hard goal. So it doesn't only achieve, it achieves the hard goal both when I have the goal, when I have the original soft goal and when I don't have the original soft goal. So you decide whether you want to actually achieve it or not achieve it. And you have two sets of actions that do that. For deciding not to achieve the hard goal, you actually use a action called forgo, and to get to get the soft goal, you have an action called claim. So you claim the reward or decide to forgo the reward. And you might recognize this sort of compilation here from the maxsat, way of changing min to max. And so because of this, we need to actually add cost for not having the goal and give 0 cost for actually having the goal. So again, the basic compilation is to generate a hard goal, create for the action forgo, the action that forgoes having the soft goal. You give it a cost equal to the reward of the goal. It takes having not having the goal as its precondition, and it gives the effect of actually having this hard goal version. There's a 0 cost version that's called claim that takes G as a precondition and just gives the effect of having the hard goal. And then we use this max to min conversion like in the maxsat method. So the other compilation trick comes pretty much exactly as our MDP compilation, where we have this done space. This is, if you're going to have an optimal planner, you don't actually need this set, because the optimal planner should, from this part of the compilation, give you an optimal solution. But if you don't have an optimal planner, it's very nice and very good for search if you're going to use a heuristic search planner. If you actually create a done space, this is a separate space of the problem where you say you're finished with the problem and you now just want to evaluate your rewards, and so you create this done space that actually evaluates your rewards. And this compilation is similar to compiling PDL, also compiling PDL simple preferences into partial satisfaction planning. And it was done in, variations of this were done in Yo-Chan PS and Yo-Chan COS. Yo-Chan PS was in the IPC 2006 competition and competed in this track called the Simple Preferences track of that competition. It got a distinguished performance award. So now I'll talk about just net benefit planners. So these are planners that were explicitly made to handle the net benefit planning problem. I'll go over, I already went over HSP star P, but I'll go over Gamer, SAPA PS, Spuds, and Bebop LP. The only of these that were in a competition were HSP star P, Gamer, and then SAPA PS via Yo-Chan PS. Yo-Chan PS is just essentially uses SAPA PS to solve for simple preferences.
What is the downside of this compilation that you've just shown? It seems like it's good. I mean, it seems like it eliminates. I mean, as long as the reward is additive between the goals, but are these?
Yeah. So it's not clear if what the downside is. There have been some. I mean, it's sort of just becoming something that people are starting to experiment over. And I'll show at the end exactly what the performance of these various approaches looks like. But in fact, from the latest research note, it looks like if you use the compilation and use the cost optimal, the winner of the cost optimal, or sorry, the satisficing track of the planning competition, so the winner of the satisficing track of the planning competitions, which had costs involved in it, that it actually does do pretty well, and it looks like it right now is a winning proposition. But it's not clear whether you could do better using specialized approaches for net benefit. It's just not clear because we haven't, of course, explored all of the specialized approaches yet. But of course, it's very appealing because you could just compile it away and throw it to your cost-based planner.
Seems like these two problems are equivalent: cost optimal planning and additive reward net benefit, right?
They are. They're equivalent in terms of expressivity, yes. But just like when you have a compiler where you give directives to the compiler as to what you're thinking, perhaps giving the actual soft goals might be a better idea. And you don't really know if that's going to be the case or not for your given domain. Right now, it's just not clear. So the first planner I'll go over is kind of if you were going to create a planner that that did state-space search, the first thing that you would do is perhaps the kind of the easiest thing to do would be to do like a breadth-first search. And the Planner Gamer, on top of various tricks that it performs, does a cost-based breadth-first search. So it does breadth-first search over cost. So each layer ends up being a cost value rather than a depth value. And so this is a bidirectional planner. It uses what's called a perimeter search, where it does first a regression search, so it does a regression search from the goals, finds a perimeter, so finds a fringe, and then from there it does this for up to some depth or to some time limit, and then from there it does a progression search and tries to have the two states meet. Once the two states meet, you essentially have a plan, is the idea. There's a little bit of a caveat, though, when you're doing that benefit planning with it, and that is that you can't prune rewards on goals because it changes the cost monotonically. So if one state looks like it's more costly than the current best state you have, that doesn't necessarily mean that you can prune it away, because you may end up, it may end up being that state could lead to an even better plan, because maybe you can achieve more goals if you just continue along that path. So it's essentially the same as its cost-based version, except for it has this thing where it actually doesn't prune away goals. The next planner is SAPA-PS. SAPA-PS is a planner that was first done in one of the first papers on partial satisfaction planning, and then subsequently I wrote a bunch about it in a JAIR paper. And so what it does is it does a search, and it does something like what Untitled does, at least in spirit, is it tries to select a set of goals during the search. So it takes each individual goal, looks at each individual goal, and then sees whether the net benefit on each individual goal is positive. If it's positive, then it selects that goal. If it's negative, then it doesn't select that goal. It's a very straightforward approach to doing selection over the search. So SPUDS is an expansion of this idea. And what SPUDS does is, rather than selecting each goal individually, it creates an IP for the goal selection. So the goal selection, the entire relaxed plan, becomes an integer program. And the integer program decides which